Thank you, everybody. I would like to thank the organizer for this nice workshop and for having me here today. I'm currently a postdoc at Laboratoire d'Informatique de Paris 6 in Paris. And I'm going to talk about some work I did with, in collaboration with Giulia Ferrini, who is now in Sweden, with Frédéric Grossens and Damien Markham in Paris. So I'm going to talk about secret sharing, and I'll start just by defining what this means to give you a taste of what's going to happen in the next slides. So basically, secret sharing is a primitive for a cryptographic primitive in which someone who is called a dealer has some information that wants to share with a group of players in such a way that no single player can retrieve the information alone. So players have to collaborate in order to retrieve the original message. And this is easy to understand with a classical example, I think. So imagine Alice has this information, classical information encoded in one string of bits, which we take here to be very simple, just a string of ones. And she wants to send it to Bob and Charles in such a way that none of the two can retrieve the original string alone. So in particular, she wants none of the two to have any information about the original string. So she doesn't want to cut the string and just send different cuts to different people. So what she can do is to generate some random string B and perform the sum modulo 2 with her own message. And this will create a third message C. And both messages B and C will look like random strings, because B is a random string and this is a random string plus the original message. So none of the two have information, but if they collaborate, if they cooperate, they can perform the sum modulo 2 and they can get exactly the original message A. So this is like a paradigm for secret sharing, and this allows me to introduce some notation, some nomenclature. We can introduce the phrase access parties for the subsets of players that are allowed to retrieve information, and we can introduce the adversary structure, which is the set of subsets of players that are not allowed to have any information about the secret. And in particular, I will be talking about threshold schemes, in which any group of K or more players should be allowed to retrieve the original information. And of course, I'll be talking about quantum secret sharing because it's in the name of the conference. So now you can have several paradigms for secret sharing. You can have classical schemes. You can have hybrid schemes in which you want to share classical information but using a quantum infrastructure. And then you have a third regime in which you want to share quantum states, of course, using quantum resources. And this is the regime I will be talking about. So there's been quite some work before. In particular, the scheme in the classical case were introduced in the 70s, and then there were proposals first for discrete variable systems, or for qubits, which were then generalized to the case of cluster states. Let's say systematized for the case of using cluster states. And then there have been proposals using continuous variable systems, which is the domain in which I work mainly. And in continuous variables, also experiments have been performed. And at some point, Damien Markham with Peter Van Locke came up with a protocol using continuous variable cluster states. So looking at all this work, which is, of course, just a partial list of the work, you may wonder, okay, so what's new in this work I'm presenting? And what's new is that I introduce a kind of random encoding to this scheme. Because you can see secret sharing is a kind of error-correcting code, as we will see later. And the schemes existing in a continuous variable case earlier were only based on very specific resource states, so very specific infrastructure. And I will present a result that basically says that almost all transformations in a certain class can do the trick. And so you can still ask why someone would care about this. And there are several reasons. So if you're an experimentalist, saying that every transformation in some class is good means that you can probably do some experiments on it. So you can tune your experimental setup to do this. Also, this can be useful for technological tasks, because if you have a class of transformation from which you can pick any and it works, then you know that you can optimize. So you can use this, for example, to share some interesting resource states. And also, it has some interest for fundamental problems, for example, in black hole physics, because especially in connection with the information paradox with black holes. Because, as I said, secret sharing can be interpreted as some kind of error-correcting code. And in particular, random coding has been used to show some results, to have some insights on how fast black holes can release information, for example, through Hawking radiation, if you use error-correcting codes. And most of them required some random encoding, which wasn't present in the case of continuous variables before. So I've been talking about this. I'll be talking about squeezing. So let me introduce continuous variables, because I assume most people are familiar with quantum information using qubits, so discrete variable systems. This stands for systems that are described with finite dimensional Hilbert space, like qubits. By contrast, I'm working with continuous variable systems, which are described in infinite dimensional Hilbert spaces. For example, the modes of the electromagnetic field. And in this case, the observables, which are more interesting, are akin to position and momentum, like the quadratures of the field. And in this case, you have this infinite dimensional Hilbert space, which is the most interesting one, which is just the space of square integrable functions. You have trivial examples. For example, for qubits, you are used to think in terms of spins, whereas in continuous variables, the main system you are dealing with most of the time is a harmonic oscillator, so a particle in a harmonic potential. And there are analogies in quantum optics. For example, for qubits, you can think of the polarization of a single photon. And for the continuous variable case, you can look at the fluctuations of the quantum amplitudes of the field. So in the classical case, you have a complex amplitude associated to the field. You can then quantize it, and these will have some fluctuations, and the classical real and imaginary parts become operators. The classical and imaginary part of the field become operators which behave in many ways like position and momentum. So you can picture all the remaining slides. You can think of the remaining material of the slides as in terms of either harmonic oscillators or modes of the electromagnetic field, which also represent the main experimental platform on which the results may be tested. So in discrete variable case, you have ways to picture the state, for example, the Bloch sphere. You have some analog in continuous variables, which is given by the Wigner function, which is also a useful mathematical tool. And basically, you can associate one such function, one Wigner function, to each state of the system, really to each well-behaved operator. And this Wigner function, we have some properties which make it similar to classical distributions over phase space. For example, if you integrate over one variable, either position or momentum, then you get the conjugated probability distribution. But it also has some purely quantum features. For example, it may be negative for some states, and many interesting states are negative. But there is a class of states which is very interesting and still has a positive Wigner function, and this is the class of Gaussian states, which is naturally defined as these states that have a Gaussian Wigner function. In particular, you may have the vacuum state, which has symmetric fluctuations in position and momentum. And you can also have squeeze states, and these are very interesting. And this can be obtained from vacuum by squeezing the noise in either quadrature. And because of the uncertainty principle, you need to amplify the fluctuations in the conjugated one. And these states are very important because, well, basically they can be in the limit. They can become eigenstates of either position or momentum, because if you imagine you squeeze the fluctuations in positions, at some point position will be perfectly defined. So it's going to be an eigenstate of position, which is useful to do calculations, but also it's a workhorse for continuous variable quantum information, because these states can be produced deterministically, and they can also be used to produce entanglement. So you can do, while in photonic systems you need to produce photons, which happens only probabilistically. In the continuous variable case, you can produce these entangled states based on squeeze states in a deterministic way. And also you can, in particular, use them for quantum teleportation, and you can use them to produce cluster states in experiments. And these cluster states are important because they have been used to translate many results in discrete variables to the continuous variable case, for example, measurement-based quantum computing, but also secret sharing at some point. So these cluster states are worth some more definition. You can obtain them in the ideal case from an infinitely piece squeezed state, so an eigenstate of, of the momentum operator by applying some operator, which is an entangling gate, which is the equivalent, the continuous variable equivalent of the controlled Z gate. And these states can be represented as graphs, where each node is one mode or one harmonic oscillator, and links represent the entanglement. And this can be represented in the ideal case as eigenstates of a set of operators called nullifiers, which are these combinations which you can derive by inspection of the graph. You see here, for example, for node 1, you have a momentum of 1 minus position of its neighbor, and even if you take, I don't know, 3, you can take momentum of 3 minus the position of 2 minus the position of 4, and so on. And these states can be approximated by Gaussian states, which can be produced deterministically. And this can be done by replacing these infinitely squeezed states with finitely squeezed ones, where the finite squeezing will result in computational errors, in logical errors which are small enough if you have a large enough squeezing to be dealt with by concatenating some qubit error correcting codes. So as I said, any Gaussian state can be produced deterministically, and in particular, any Gaussian pure state can be produced from vacuum by applying some multimode squeezing transformation. So you squeeze each mode, and then you mix the modes in some passive interferometer. So just you produce a network of beam splitters and phase shifters, and in the end, if you tune the parameters well enough, you can produce any Gaussian state in this case. So this is about all the machinery I need to introduce the results. And these results have been on the archive for a couple of months. You can have a look at the preprint if you want. And basically, a bit of synopsis. We arrived at these results through a kind of a peculiar path, which I find interesting, which was, there was this experiment producing approximated cluster states, and we wanted to see if we could do some interesting protocols with it, and we tried looking at secret sharing because we knew Damien, so we had some expertise in this. So we started from a theoretical protocol, theoretical primitive, which was based on cluster states, which was then modified for the experiment. And in this translation, some of the key features of the theoretical model were lost, but the experiment somehow still worked. And trying to figure out why the experiment still worked, we arrived at the main claim of this presentation. So I will just describe briefly how this works for cluster states. Imagine you have these cluster states where each node of the graph is a mode of the electromagnetic field, and then you have some secret state which can be anything. So as I said, this pentagon can be written as some eigenstate of a class of operators which are the nullifiers corresponding to the graph. And then you want to basically teleport the secret onto the ring so that you have then 5 modes that you can share with players, and they will be able to reconstruct the secret in some way. So what you do is you start with these 2 unentangled states and you perform a continuous variable Bell measurement. And as a result, you will have this state with 5 modes, for example. And now all the information about the secret is encoded, is delocalized on the pentagon, which means that basically this pentagon can be written as in this form, where it is still an eigenvector of an eigenstate of the nullifiers, but no longer corresponding to the eigenvalue 0. And basically, you can introduce a set of logical operators, for example, any of the nullifiers, and this sum of all the 5 position operators of the modes on the ring. And these represent the logical operators in the sense that if you measure them, then you get the same statistics that you would have if you measured either the position or the momentum on the initial secret state. So the information is delocalized, and the point is now trying to reconstruct the information in some access parties. And this scheme is used to perform some threshold scheme, which is a 3-5 threshold scheme. So with 5 players, in which any group of 3 can reconstruct the secret. And in the theoretical model, this followed from the properties of the graph states that allowed you to show that any of these 2 logical operators can be written in terms of only operators from any 3 players. So as I said, this was generalized to the experiments. This was translated to this setup using optical frequency combs that produced some wide spectrum field, which was a multimode squeeze state. And then we tried to simulate the protocol, basically measuring the noise that would be caused by the finite squeezing and not by having a finitely squeezed cluster states and not the ideal one, and assessing whether this noise was low enough to improve on the communication, on the reconstruction quality of the secret with respect to any classical scheme. And this was possible, but basically the protocol, as I said, was simulated because there was no way to really physically separate the different modes and send them to different parties. So we were trying to see if we could generalize this and to see whether we could find a general way a systematic way to write all possible secret sharing schemes that can be done in a continuous variable case. So we just started with this abstract model where you had these squeeze modes and the secret, and you assume you can mix them in some interferometer. And then the dealer, one mode which we call the dealer, measures some quadrature, for example, the momentum quadrature on the first mode, and gets an outcome M, which is then broadcast to all the other players. And in this way, the information should be delocalized on the modes which were initially squeezed. And then we tried to write down what conditions should the interferometer satisfy in order to define a correct secret sharing scenario. So which were the conditions on the interferometer such that we could derive some decoding conditions and write the logical operators in terms of local operators. And it turned out that basically there is almost no restriction on the interferometer, or better, there is some restriction, but almost all interferometers, so almost all physical setups, satisfy these conditions. And this can be made precise in the sense of Haar measure. So I will just give you an idea of the proof. I'll spare you the derivation, even if it's quite simple, because I don't have much time. But basically, this just involves modeling, describing the Gaussian operations as symplectic matrices. And this can be done because if you organize the position and momentum operators in a single vector, then you write down their commutators, and you see that they are related to this matrix J, which is called the standard symplectic form. And basically, if you look at unitary Gaussian transformations, their action can be written as applying a symplectic matrix. So their action of Gaussian transformations in the Heisenberg picture boils down to applying some linear transformation to the input quadratures. And the output quadratures will still satisfy the canonical commutation relations, and this means that the matrix S has to be symplectic. And in particular, there are two relevant classes of symplectic matrices which correspond to physically important transformations, and these are the diagonal matrices, so diagonal symplectic matrices, which basically mean you're doing squeezing, you're either elongating or compressing one of the axes, so you're doing squeezing. And the other class is the linear optics. It's the one that corresponds to passive interferometers or linear optics transformation. And this class in particular is also isomorphic to unitary matrices. So if you have a linear optics transformation on n modes, this boils down to, this is in some correspondence with a unitary matrix n by n. And here comes the connection, we see later, here comes the connections with the Haar measure and the statement that almost any interferometers can do. So basically, if you take another look at the setup, you can start with the quadratures in the beginning, and so you will have the quadratures for the secret, and some quadratures in the vacuum mode. Then you apply squeezing on these quadratures which were initially the vacuum, and then you represent the interferometer as the action of this symplectic matrix. And then you can model measurement by just replacing the measured quadrature with the number m in all equations. So now to see how you can decode the secret, you can look at what are the local quadratures of each player. So each player will have two of these quadratures, one for position and one for momentum, which is just a linear combination of the input ones, where here I separated the secret quadratures and the squeeze quadratures. And basically, we assume that we do squeezing in the momentum quadrature. So these things, in the limit of infinite squeezing, can be neglected. And these things correspond to having a flat probability distribution summed to your measurement results. So these things will contribute to the statistics with the Gaussian, which is larger and larger as you increase the squeezing. So you want to get rid of these things because they will blur your secret statistics in the limit. But you want to solve the system for these things. So basically, finding the decoding conditions boils down to solving linear systems. And in particular, this can be done if you can show that some submatrices of the symplectic matrix L are not singular. And this can be written as polynomial conditions on the coefficients. And here is where the Haar measure comes into play, because so here I just written the conditions that you have to satisfy in order for one access party to be able to reconstruct the secret. And you see there is the determinant of some submatrix which is non-zero, and this other element which should not be zero. Now, Haar measure may seem something very abstract, but you can picture it in a very simplified manner as some uniform probability distribution. Basically, you know that you can write unitary matrices as points on a sphere, on a multidimensional sphere, and then you can parameterize it with some functions of the angles, and the angles live in some region of Rn squared. Now, the Haar measure is just you can think of it as just a flat probability distribution on the sphere, and you see that. Basically saying that almost any interferometer will do is the same as saying that the bad ones correspond to a set of zero measure on the sphere. And you can prove that the set of bad matrices has zero measure fairly simply because, as I said, these conditions are polynomials in the coefficients of the interferometer SL. And so they are real analytic functions of the angles. So basically functions that can be written as a power series. And with real variables, you have a similar result as in complex analysis, where you know that the zero set of some analytic functions must necessarily have zero measure. So basically, with all these ingredients, you can easily show that this is also the case in the real for real variables, and you can easily show that the set of matrices which do not satisfy this thing has zero measure. So the set of good interferometers is almost all the possible interferometers you could use. So what does it mean that you can decode? It means that you can write that you can solve. You can write a linear combination of quadratures of the access parties that correspond to the secret ones. So you can sample from the probability distribution of the secret quadratures just by doing local homodyne measurements. And this also implies that you can physically produce a transformation that leaves one of your modes, so one of the modes of the access party, in the secret state. So this is basically all I wanted to say. Just what I showed you was a general scheme for Gaussian, for secret sharing in continuous variables with Gaussian resources, and this works for almost any passive interferometer. And okay, I'll just leave you with the summary. Just the decoding also requires only a Gaussian operation, which is nice, and the decoding transformation can be computed efficiently for each access party, and the decoding is pretty cheap in terms of experimental resources because you can realize it with a limited number of squeezing operations, or you can even only do local homodyne detection. So you can do a tomography of the secret by having each player just measuring its share and then sharing the results. Okay, so last thing to mention maybe is that I showed you here the case in which the secret was just a single mode, but you can generalize this to arbitrary number of modes in the secret. And there are still some things that we are working on, like characterizing the output, the reconstruction, the quality of the reconstructed state in terms of capacity of the channel defined by the encoding and decoding. And then we are also looking at, we are having a closer look at how easy it would be to implement these schemes by looking at whether this is robust to losses and whether we can optimize the interferometer, and we are kind of optimistic on these two last points. So thank you for your attention.
Hello, questions?
Hi. Well, as an experimentalist, I will ask a question about the very short period where you mentioned the experiment. So you talked about the pentagon and then the frequency modes, right?
Yes.
What those modes 1 to 6 look like?
So I guess this is the experiment you're also familiar with. So the squeezed modes here, so before becoming the pentagon, before you combine them, they look like Hermite-Gaussian modes. So basically they have a Hermite-Gauss spectrum. Mm-hmm. Then, as I said, you can approximate this cluster state with Gaussian states by just mixing these modes in an interferometer. Or equivalently, you can think of the interferometer as a linear combination of the modes. So you change the quantization basis to a different one. So basically you look for the frequency comb example, you look at different combination of these spectral modes. Mm-hmm. And this linear combination of the squeeze modes, which have this Hermite-Gauss spectrum, will be the nodes of these things. And generally, the nodes of these things have overlapping spectra, so you cannot separate them with linear optics. You cannot just send them through a prism and separate different frequencies.
Okay, those are not just the different regions of the spectrum. They are the overlap, actually.
For this experiment, they were not. We did some optimizations to try and have the nodes of the pentagon as different slices of the spectrum. And we have some results to improve that, but I don't think the squeezing of the reconstructed supermode would be high enough to do secret sharing.
I see.
At least not with this scheme.
Okay, thank
you. We have time for just one question.
This question is coming from the opposite end of not experiments. So what I do looks very different from what you do, and I'm generally dealing with full field theories. And so what it looks like to me is you have a cutoff at some point, because I saw some sums here that were up to the nth mode. And I was wondering what you could say to what that cutoff means about the frame of relevance of what you're doing.
The frame of?
The frame of relevance, like what approximations do you have to make in order to ensure that that cutoff isn't going to affect the causality of what you're doing or something like this? Okay. Or if that's something that's just beyond and totally irrelevant.
So basically, if I understood the question correctly, it's on the number of modes you can have in the protocol. So there's no restriction on the number of modes as long as you have energy, because basically when you do squeezing, you increase the energy of the system. It requires interaction. In the optical case, it means interaction in a linear crystal with some classical field. So to increase squeezing, you need to have stronger classical fields. And this for each of the modes. So at some point, you will run into a problem with the energy, because the energy required to produce such squeezing will be bigger than the energy you have available. And this is actually one of the points I would like to investigate in the future, because I mentioned the connection with black holes, because there are basically results. There have been papers looking at black holes as Gaussian channels, and then you look at the capacity. And when you do continuous variable quantum information, then you look at energy constrained capacities, because otherwise you could encode. If you didn't have any restriction on the energy, you could encode an infinite number of symbols, and then things kind of don't make sense anymore. But this is something I would like to look into in the future. So thanks for the question.
Okay, let's thank Francesco again.